In this video, we're going to be looking at systems of differential equations with imaginary eigenvalues. It turns out that these have something to do with rotations. So I'm first going to start with a rotating system, and then we'll see how a system with imaginary eigenvalues arises. First, let's build a unit circle, and we'll draw a vector, and if we call this angle t, then the xy coordinates of it are given by cosine t sine t. Now let me write down a matrix. This matrix would be cosine t minus sine t cosine t. And let's see what it does to the vector 1, 0. Well, multiplying it out, we see that we get cosine t sine t. So we should think of this matrix as rotating vectors by t radians. Now I want us to do a little thought experiment. In order to not clutter things up, let me call this function p of t. I want us to answer the question, what does p prime of t equal? Well, of course, since we know p of t is the pair cosine t sine t, we could just take the derivatives. But I want us to answer this question geometrically. If p of t represents the position on the circle, then p prime of t will be your velocity, which will be tangent to the circle. Now if you imagine me parallel transporting this vector down to the origin, we see that the relation is that p prime of t is equal to p of t rotated 90 degrees. How do we rotate a vector 90 degrees? Well, we use our rotation matrix and just plug in pi over 2. So computing this out, we find that p prime of t is equal to this matrix 0, negative 1, 1, 0 times p of t. So this differential equation has something to do with traveling in circles, and this is the equation we're going to be looking at as our primary example in this video. Now we're going to approach this from the opposite direction, where we start with a system of differential equations and try to derive the solution. We're going to use the previous system, so we have x prime y prime is equal to 0, negative 1, 1, 0, xy. The algorithm we use to solve this is the one you're probably familiar with. First we find the eigenvalues, then we find the eigenvectors, then we have this formula for the general solution to the differential equation. Let's go through and solve this differential equation. To find the eigenvalues, we subtract lambda off from the matrix and compute the determinant. This gives us the characteristic polynomial of the matrix, and the eigenvalues are the roots of this polynomial. So the roots are lambda is equal to plus or minus I, and we see that in this example we have imaginary eigenvalues. And don't worry about them being imaginary, you follow the exact same process that you do when you have real eigenvalues. We now find the eigenvectors using the usual method. I'm going to just put lambda in here for now, and then plug in the actual value of lambda at the end. It saves me from needing to do the computation twice. Anyway, we look for vectors in the kernel of the matrix minus lambda, so we find some vector w1, w2 such that this is equal to 0. We can compute this out, and remember, you can't solve for both coordinates since you don't just have eigenvectors, you have entire eigenlines. I'll choose the top equation, and this tells us that w2 is equal to negative lambda w1. Since by assumption our eigenvectors are the pairs w1, w2, we now sub in negative lambda w1 for w2, and if we factor off the w1 component, we see that the eigenvectors are scalar multiples of 1 minus lambda. Now we can write the general solution x of t, y of t, which is some constant c1 times e to the it. And since this is for the eigenvalue I, we plug in I for lambda, so our vector is 1, negative I. then our other solution is c2e to the negative it 1I. I want us to take a moment and look at the solution we just derived. This was computationally easy, we just followed an algorithm and it spit out a solution. But remember, this differential equation that we started with was something about traveling in circles. Our original solution to this equation was x of t y of t is equal to cosine t sine t. I want to rewrite our general solution such that it becomes manifest that there are particular solutions that look like the original solution, cosine t sine t. I'm going to call this the real form of the solution. So first I'm going to go through and convert it to real form the hard way. I'm going to speed up the video here because there's nothing clever going on. I'm simply using Euler's formula and renaming constants to get it in this new form. It's just an exercise in arithmetic and algebra. We end up finding that the general solution can be written as some c3 cosine t sine t plus c4 times sine t minus cosine t. And you can see how our original solution now fits into this story. Now that we just used brute force to convert our solution to the real form, let's see how we can use an observation to make this process a little easier. First, let's just rewrite the two forms of our solution. I want us to focus on the term e to the it 1 negative I. Now I'm going to use Euler's formula and expand this term out, and let's see what happens. We get this vector cosine t plus I sine t minus I cosine t plus sine t. Let's split this into real and imaginary parts. We now have that this solution is equal to cosine t sine t plus I sine t negative cosine t. I want you to notice that the real and imaginary parts of this one solution can be used to form a basis of real solutions. This gives us a fast way to solve these types of equations. Now I'll explain the algorithm of converting complex solutions to real solutions via this fast way, and then I'll show you an example. The premise is that you have some system of differential equations like this, and these numbers a, b, c, d are all real, and it's important that the eigenvalues are not real. They can be pure imaginary numbers like plus or minus 2i or 8 plus or minus 3i, but this method does not work if you have eigenvalues like 2 and 7. And by the way, if you're wondering, if all of your coefficients a, b, c, d are real, then the eigenvalues actually have to come in complex conjugates if they're not entirely real. So the method starts off like normal. You'll need to find the eigenvalues, obviously. Now assume you found both eigenvalues. You can go ahead with the brute force method where you find both eigenvectors and write the general solution and then convert everything into cosine and sine. That will 100% work, but this trick requires less work. So now you really only need to find one eigenvector. It doesn't matter which one, just choose one of the eigenvalues and find one eigenvector. You aren't going to need the other eigenvector anyway. Once you have found the other eigenvector, for example, the eigenvector v1 corresponding to lambda 1, if you find the real and imaginary parts of e to the lambda 1t v1, this generates the real basis of solutions to your differential equations, and then you're done. I'll show you with an example. Say you're asked to find the real form of x prime, y prime is equal to -1, -4, 1, -1, xy. We start off by finding the eigenvalues. That is, we take the matrix, subtract off lambda, compute the determinant, and set it equal to 0. In this case, we find that lambda is equal to -1 plus or minus 2i. Now we move to step 2, where we realize we can save some effort by only finding one eigenvector. I'll choose to find the one corresponding to -1 minus 2i, but either one will work. So we take the matrix, subtract off the eigenvalue, and find the vector v1, v2 that gets sent to 0. We can choose either equation. I'll choose the bottom one. This implies that v1 is equal to -2i v2, so we see that our eigenvectors are of the form v2, -2i, 1. Now to step 3. We need to find the real and imaginary parts of e to the -1 minus 2it times -2i, 1. I'll factor off the e to the negative t and then use Euler's formula to convert e to the -2it into real and imaginary parts. I've run out of room, so let me continue this computation on a new page. So picking up where we left off, we have e to the it, -2i cosine t minus 2 sine t, cosine 2t minus I sine t. We factor this into real and imaginary parts to get the vectors e to the -t, -2 sine t cosine 2t, minus e to the -t, 2 cosine t sine t. And don't worry about if it's a negative or a positive in front of that I, it doesn't matter, because remember, we can multiply solutions by any number and we still have a solution. Using these terms, we now have a real basis for the general solution to the differential equation. In real form, we can write the solution as x of t y of t is equal to c1 e to the -t, -2 sine t cosine 2t, plus c2 e to the -t, 2 cosine 2t sine 2t. And that's where I'm ending this video.